Hello everyone, my name is Dilip. I work for Google, and today I am going to talk about global indexes in PostgreSQL, which is not yet committed. It's in progress feature. And I'm mainly going to talk about the design decision we have taken while working on this feature, and the key challenges what we have faced, and based on that how we have changed some of the design decision. And also I am going to talk about the open challenges we still have, and because of that the feature is still not yet in the PostgreSQL code base. This is a quick introduction about me. I am PostgreSQL listed significant contributor. I am working on PostgreSQL code base for almost 18 plus years now, and I am member of program committee of PGConf.dev and PGConf of India, this conference. The couple of key contributions what I have made in PostgreSQL over last 10 years are in parallel query, like parallel bitmap heap scan and parallel merge join. Some improvement on logical replication, namely logical replication support for in-progress transaction. Also, my latest work was in PG17 related to SLRU performance improvement. And in past, I worked on Alger for compression, support for Toast, and the wall log create database. Currently, I'm working mainly on the config log history table for conflict detection in PostgreSQL, and some research on, or some weekend research on global indexes. Okay, this is going to be the agenda of my today's talk. First, we'll start with why do we need global indexes? And then we'll talk about the high-level design goals. And then most of the design part, what we'll discuss will be based on that design goal, what we have decided. I'll also talk about why we have chosen those design goals. Then we'll see the storage selection we have taken for global index, how we have implemented attach and detach partition, how the global indexes work. And with that, I think we will be done with the first part of the presentation. And then I'll move into the key design challenges, which are still open. And we have a couple of potential solutions, but I'll say the solution for them is not yet submitted anywhere in the community. But the first part of the presentation, what you see is the most of the code is submitted as a patch in the hackers list. Okay, we are back on track. I'll start with the example that why do we need a global index. Many users who are coming from Oracle, they must already be aware that why they need global index. But for PostgreSQL user, I'll just start with the example. So you can see a simple example where I'm trying to create a table, and this table is partitioned on the region column. And it have two partitions. One is for the user on the US region, and other is for on the Europe region. And when you try to create a unique index on that, any other column which is not part of the partition key, it means this table is partitioned based on the region column, but I am trying to create a unique index on the email column. You'll see this error that unique constraints are not supported, or it should have all the partition key involved in the index. That means the problem is that you cannot have a unique constraint on a non-partition key column. So within a region, you are allowed. You can have a unique index or unique email ID within each region, but across region, you cannot have an email ID, right? That's not a great situation. And most of the business cases where people might want to have your table partition on some of the column, but uniqueness on other column as well. So that is quite restrictive. And there are a couple of solutions what people are trying around, or what they can do to resolve this issue. One option is don't use the partitioning at all. It means you can just remove the partition by clause itself and have one big table. You can do that, but then you will not get advantage of what we are getting with the partitioning. The partitioning pruning feature and everything will not be usable then. In some cases, you can use application level logic to ensure application logic to ensure the uniqueness, but that is prone to error, and sometime performance issue can also be there. Some people chose to migrate to other databases where they have global indexes, or actually it's opposite, that people who are on Oracle or any other databases where they are using a global index, their partition strategy is based on the global index, they do not migrate to PostgreSQL, and that's not good as a PostgreSQL community. So the last solution, what we can do and what we are trying here is to implement global index on PostgreSQL itself. Okay, so these are the high-level design goal I had in mind, or a couple of folks involved in that design had in mind that what we want to do to have the successful global index in PostgreSQL. First part is we want to use the same B tree, whatever is there in PostgreSQL for the local indexes, and we don't want to change a lot of design around the B tree. It means you don't need to maintain a separate data structure or different B tree for the global indexes. Instead, we can use the same B tree. So we'll see a lot of design decisions we will take around will be trying to meet this goal. And second goal is, currently if you detach or drop a partition from the partition hierarchy, you don't need to do anything, right? Because all partitions are separate, indexes are local. When you drop the partition, indexes is also getting dropped with that, or you detach the partition, indexes is also getting detached from the partition hierarchy. But when you get a global index, the problem is different, right? Because the global index is holding the data from all the partitions. And if you are detaching a particular partition, or if you are dropping a particular partition, how will manage those data? One option is that you try to clean up those data from the global index, but we do not want to do that. We don't want to put extra overhead on the detach or drop partition. So that is the second design, high-level design goal we have. We'll discuss later in upcoming slide how we try to meet this goal while working on the design. This is the global index storage decision what we have taken. So if you see a local index, a B tree index, what each tuple contain, it contain a key and TID pair, right? Key is nothing but the column on which you created the index, and TID is a locator in the heap, which is nothing but the block number and the line pointer in the heap. And the tuple are also stored in the order of key and TID. But if you talk about the global index, TID alone is not sufficient, right? Because TID is block and the line pointer. But in global index, you have multiple partitions. You need something extra than the TID, right? Because the TID can be duplicate across the relation. So we agree that we need an additional identifier to accurately locate the tuple within a partition. And in upcoming slide, we'll discuss about what that identifier can be. But in short, what we understand is we need the relation ID, relation OID, then the block number and the line pointer to locate the tuple, right? If there are multiple relations are there covered by the global index. I still kept as a partition identifier because we'll discuss why we cannot use a relation OID. And for storing in this format, there are multiple options. We can have a different way of adding this partition identifier in the tuple. But we chose to keep that partition identifier as a last key column. And the reason for that decision is the first goal when we say that we do not want to have a lot of changes in B tree format. A lot of optimizations are there in B tree format with respect to deduplication and the suffix truncation. I'm not going to go in detail of all. But when you add a partition identifier along with the last key column, then you'll get all this advantage without doing any extra effort. So yeah, that is the long topic, and we can maybe discuss some other time. So let's see, what is the partition identifier we have chose? Ideally, we need a relation ID, right? We want a relation ID of the partition, and in that we want a TID. But we cannot use a relation OID because of the second high-level goal, what we talk about, that we do not want to clean up the global index the tuple inside the global index when we are detaching or dropping the partition, right? So thing is that the relation OID can be wraparound. If you drop a relation, the OID is 32-bit number which can wrap around and can be used by any of the other relation as well. And second part is you may detach the partition from the partition hierarchy and may reattach it. So problem is that if you leave the tuple in the global index, don't clean up the tuple, what will happen when you detach and reattach the same partition? It will come with the same relation OID. It means you will not distinguish between the tuple which was previously there in the global index versus the newly there in global index. So you don't know how to ignore the older tuple. Because of that, we cannot use the ID which is constant or can be wrapped around and assigned to some other relation. The solution what we have chosen is we have created a new identifier which is called a partition identifier, which is completely unique. Although we need a mapping to identify from partition ID, if you locate in the tuple in the global index, you need to know which relation this partition ID belongs to or which relation this partition ID point to. So we need to store a mapping in the catalog which is PG index partition, although we maintain the cache over this catalog so that the searching or mapping is faster. And every time your partition is getting attached to a relation or a partition table on which global index exists, we do allocate a new partition ID. That means the problem what we have of reattaching, detach and reattaching is resolved, right? Because every time you get a new partition identifier, whenever you attach the partition. It means you can differentiate between the older tuple and the newer tuple. Older tuples, the partition ID will be invalidated, and the new partition ID will get when you attach. It means when you see in index the tuple which belongs to some partition ID which is invalidated, you can just ignore them. We'll talk about those when we go to the global index scan. Okay, there is one more problem along with what we have just discussed related to that we cannot use a relation ID and we need a partition identifier. But can we just have a one partition ID for a relation at a time? If you are attaching a relation to a partition hierarchy, can you just allocate a single partition identifier, even though it is part of the multi-level hierarchy of the partitions? If you see this diagram, in that we have a top-level relation which is we are saying as a sales data. Under that we have three partitions from the different region, America, Europe, and Asia. And under that again we have a different sub-partition for the different country, E and G you can say. And imagine the case you have a global index on the top level partition table as well as the second level partition table. Now, if I use a common partition ID for this leaf relation, so one point to be noted that only we use a partition identifier for the leaf relation because only leaf relation contain the data and you don't need anything for the intermediate relation or the top level relation because they don't have any data. So if I allocate a single partition ID for any of the relations, for E partition, if I allocate a single partition ID and I insert the tuple in both global index, a top level global index as well as the second level global index, and if I detach that partition, whole hierarchy, you can see the cross red mark, I have detached that whole partition hierarchy. It means the partition E and G need to remain attached to the global index at the second level, but they're supposed to get detached from the global index at the first level. But if I have a single partition ID and if I invalidate that, it means it will get detached from this global indexes as well. The tuple inside this global index at the second level will also be invalidated. So I cannot do that. So for that, what we need to do is at every level in the partition hierarchy, we need to have a separate partition ID for each partition table. Attaching a partition is simple. I think we already discussed that whenever you attach a new partition, you need to create a unique partition identifier for that relation for each global index in your partition hierarchy. And then you need to create a mapping in the PG index partition so that you can map from the partition ID to a relation OID. You also need to rewrite the global indexes in the partition hierarchy, because the data from the new partition, what you are attaching, or a whole new partition hierarchy you are attaching, the global index need to be loaded with those data. So either you can rewrite the global indexes, or you can find some other alternative of inserting those new tuple into the global indexes. But that is again a complicated design decision, that if you are attaching a new partition which is just containing a 1% of or 0.1% of the data of the total partition hierarchy, it's fine to insert those new tuples. On the other hand, if you are attaching a whole partition hierarchy which is containing a 50% of the data of the whole partition table, or the currently whatever is there in global index, inserting those tuples will be very costly, and compared to that, you can just rewrite the global indexes. So as of now, in current design, we are just rewriting the global indexes to not complicate it further, but there are option of optimization where if a very few amount of data is getting inserted, you can just insert those data instead of rewriting the global index. Detaching a partition is pretty simple. You just need to invalidate the mapping in the PG index partition table, which is catalog. We are keeping a mapping for the relation ID to partition ID locating. We can just invalidate that mapping. And we don't need to do anything. We don't need to physically remove the tuple from the global indexes, because that ID is invalidated. Whenever you are going to scan the global index, you'll find the partition ID, and you'll not find any mapping relation ID with respect to that partition ID. It means you'll just ignore that tuple, and later vacuum or any other garbage collector process can remove those tuple. This is how global index scan work. So when you scan a parent table on which the global index exists, we do consider a global index scan path. But on the child table, whether it is a leaf level child or intermediate relation on which the global index do not exist directly, we don't generally consider global index path. It doesn't mean that we cannot consider. We can consider the global index path. We can add extra filter that only select the tuples which belong to a particular partition hierarchy. But then the costing and are going to be quite difficult. So I think the first version we have decided to do the global index scan only for the table on which global index directly exists. How does the tuple fetch work in the global index scan? So when you scan a B-tree tuple, in global index you'll find key, partition ID, and TID. So what you need to do is you need to convert a mapping from partition ID to a relation OID by looking into PG index partition table. And once you find that relation OID, TID is sufficient to locate the tuple within that particular partition. In some of the early tests, what we have done with the global indexes, it shows a significant reduction in scan time, because when there are thousands of partitions are there, if you do a scan on non-partition key column, you need to scan all those indexes and you need to append the result of those index scans. On the contrary, when you do the global index scan, you just need to scan a single global index, that's all. So all the global index is big, larger than compared to small partition indexes. But when you do the index scans, you need to locate the key tuple, you need to traverse through the partition, the index hierarchy and come to the leaf level page. So that all extra page scan you can avoid across the thousands of different partition indexes. So one simple example we can take is, suppose there is 1,000 partitions are there, and all partitions index are there with the depth of 3. On the other hand, there is a global index is there which is quite big and of the depth of 5. So locating a tuple within a partition index will take a 3-page scan, because depth is 3 to reach to the leaf level. But you need to do that 3-level depth for 1,000 times on the 1,000 index. On the other hand, on global index, you need to just scan a 5 pages to come to the leaf page, but that is just in one single index. So that is what you can see the amount of performance improvement you will see. Okay, so from here I'm going to switch to the second part of the presentation, where we are going to talk about the design challenges we have faced while working on global indexes, which are yet completely unsolved. There are some potential solutions are there, which I am going to discuss. Okay, so I'll start with the example. I started with a table which have 1,000 partitions. Each partition have a 50,000 tuple, and I tried to vacuum that with global index and without global index. When I say without global index, you can consider it have a partitioned index. So the vacuum time increased from 15 seconds to 45 minutes. Anybody think this is acceptable if you implement this global index, which is taking, vacuum is taking from 15 seconds to 45 minutes? People will say, I'll just get rid of the partitioning and I'll have one large single table instead of having a partition table, right? Because 45 minutes are not acceptable. Your global index will never be vacuumed, and the bloat will all over there in the global index. So problem, what is the problem with that? It is very much, the problem is in the root of how we have implemented the vacuum in the PostgreSQL. So far, it might not be that bad, although there are some complaints around that as well, but with the global index, it is very highlighted. So heap and index vacuum are tightly coupled. Whenever you try to vacuum any of the relation, it do the heap pruning part first, collect the dead TID, then do the index scan, remove the dead TID, mark the dead TID is dead in the index, and then in the last phase, it will reclaim those TIDs from the heap, so that TIDs can be reused for the future insert or updates. But the problem is the global index is, when global index is there, when you are scanning any partition, you collect some dead TIDs, right? And that TIDs need to be removed from the local indexes as well as from global indexes. So global indexes, which is containing a data of 1,000 partitions, are getting vacuum for every partition. It means it is getting partitioned 1,000 times. So that is what you see the scale, that the amount of time with the vacuum increased from 15 seconds to 45 minutes, which is almost 180 times more than with the without partition global index. And the reason is that the global index is getting vacuum multiple times for every partition. So these are the couple of solutions what we have discussed in community, and we are still taking choices between what solution we should select in the first version. One very obvious solution, anybody will ask that why you are vacuuming global index 1,000 times, just vacuum it once. Yeah, that's the solution, very simple line, we need to vacuum the global index only once. Although it is not as simple as we can say, but we'll discuss the detail and what problem is there in the vacuuming global index only once. And the second part is we said, right, index and heap index vacuum are tightly coupled. So just decouple them, make them independent. So whenever your heap is ready for vacuum, vacuum the heap. Whenever index is ready for the vacuum, vacuum the index. It means you don't need to vacuum the index every time you vacuum any heap. So I'll discuss the first solution, which is vacuum the global index only once. So as part of this solution, the auto vacuum will operate as it is. It will operate on the partition table, but it will just do the heap pruning part, and it will do a local index vacuum. It will skip the global index vacuum. But what we need out of that, we need a dead tuples. We cannot lose the information of dead TIDs if you want to remove those dead TIDs from the indexes. So we'll take a dead TID store, we store into a hash map. The mapping will be from relation OID to a dead TID store. And once you are done with all the partition in that hierarchy on which global index exists, then we will do the global index vacuum only once after you have multiple dead TID store. And for claiming and reclaiming the dead TIDs from the heap, you need to do all the index vacuum. It means the global index has to be done. So only after global index vacuum is done, you need to go and reclaim the dead TIDs from all your partitions. So that is how we are doing multi-phase vacuum, but vacuuming global index only once. What is the advantage of this approach? This need just an infrastructure, or you can say it just need a restructuring of the code. No, we don't need a lot of new infrastructure for implementing that, right? We just need to ensure that when we vacuum a partition which have a global index, we need to combine those all partitions together, and we need to collect the dead TIDs, store somewhere, and then vacuum the global index. Although the code changes will be huge, but no new infrastructure we need to add. The problem is, which some committer might not think the problem, but other may. So yeah, the people have different opinion on that. The problem is that we need to vacuum all the partitions which have a global index on top of that by a single auto vacuum worker, because your dead TID store is still in the local memory. So we need to get them vacuumed by the same auto vacuum worker, which might affect the parallelism if you want. On the other hand, if you don't have global index, those partition can get vacuumed parallelly by the different worker. So that limitation we have, and my argument to that is that when you create a global index on a partition hierarchy, you may assume that as a single unit itself, although you are getting advantage of the partition pruning, but with respect to vacuum and scan, you can consider them as a single unit, and that's what we need to live with. And another problem is that in very extreme case or a synthetical case, you can create a case where assume you have 100 partitions, and every time at a time only one partition is getting ready for the vacuum. So one partition is ready for the vacuum, you will vacuum it, you collect the dead TIDs, you have to vacuum the global index because there is no other partition is ready for the vacuum, right? Because we already thought that we'll only collect, vacuum the relation which are ready for the vacuum. So for that, solving this problem, what we can do is we can push some of the relation early for the vacuuming. Suppose some of the relations are there at the 80% or 70% of the threshold near to the when they are supposed to be vacuum. We can just push them for the vacuum and get the global index also getting cleaned up. So with that, you may try to early vacuum some of the relation, but you will not have a problem of vacuuming global index multiple times. The second part, second solution is which is a decoupling of a heap and index vacuum. It means we will solve the problem from the core itself, that we will not need to vacuum index along with the heap. So for that, what we need to do, what is information we are getting from the heap vacuuming, and that is forcing us to do the index vacuuming, is the dead TIDs, right? So if we persist the dead TIDs across the vacuum cycle in the permanent storage, it means you don't need, or you are not forced to vacuum the indexes. So we try to work on that as an independent problem, and there is some couple of patches also there with providing the dead TID store for decoupling the global and decoupling the heap and index vacuum. But there are major challenges with respect to the scheduling, right? Because now you have an extra unit of vacuuming. You need to vacuum the heap as well as you need to vacuum indexes. So now if you skip the index vacuum at certain point, if they are not ready for the vacuum, when do you schedule the index vacuum? So currently we have a problem of scheduling only vacuuming the heap. Now you have extra unit that you need to vacuum the index as well when they are ready for the vacuum. Although it will give a lot of performance enhance if it is done properly, scheduling is done correctly, but if your scheduling is not done properly, then your some of the index might always starve for the vacuum and never get vacuum, so that can be even worse. And with that solution, you don't need to do anything for the global indexes, right? Because we are saying whenever heap is ready for the vacuum, we'll vacuum it. Whenever index is ready for the vacuum, we'll vacuum it. So your global index is large, it will reach the threshold very late compared to the partition index, so problem is automatically solved with that design itself. What is the advantage and disadvantage of this approach? So this is overall infrastructure improvement and benefit any other indexes and vacuum itself, not specific to global indexes. And as I told, that no special handling is required for the global indexes. The problem is it required a complete new infrastructures for storing, persisting the .tid layer, and also required a lot of changes in the scheduler. So, and if you make a changes in the scheduler and make a new scheduling algorithm, it might take time to get it stabilized over the period of time. So that can impact the whole vacuuming flow for other areas as well, not only the global indexes. The second problem what we have faced or what is still open is with respect to DDL and index rewriting. So some of the operations like vacuum full cluster, attaching a new partition, setting a different data type for any of the column, or truncating some of the partition. These all operations do trigger a global index rewrite. Basically, they trigger index rewrite in PostgreSQL, but in our case, they will trigger the global index rewrite as well. Index rewrite is not a big problem because suppose you are truncating only a single partition, the index with respect to that partition getting rewritten is fine, or it will get truncated, that is enough. But for us, global index is holding a data from multiple partitions. So if you are truncating a single partition, you cannot just truncate the global index. You need to rewrite the global index so that it do not contain the data from that truncated partition. Someone might say that you have an option, what we are suggesting for the detached partition, that just invalidate the partition ID and allocate the new partition ID. So yeah, we can do that in some cases. Suppose you truncate a relation, any partition, I don't need to rewrite the whole global indexes. I can just forget the partition ID, what was allocated for that particular partition, which is getting truncated, and give it a new partition ID. It means all the data, old data which is there in global indexes are now will not be referred ever. But in some cases, we may say that if you are frequently truncating some of the partitions, and then it might lead to index bloat, and then again, new sort of problems. What are the takeaways for our talk? So, global indexes are critical for enforcing the unique constraint on non-partition key column, and for some of the workload or some of the user, it is very hard to avoid to not have the global index, and that is one of the major problems that some user might not want to switch from Oracle to PostgreSQL. And while working on this, our high-level design goal was to have a minimal changes in the B tree so that we can utilize the same B tree without a lot of maintenance overhead. And then we discussed a couple of design challenges with respect to tightly coupled heap and index vacuum, as well as the handling of the DDL operations where we need to rewrite the global indexes. And we need to work on those challenges, and we need to explore further to deliver a robust and performant global index which can be used by the user. Yeah, that's all I had in my talk. Thank you, everyone. And